Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. My contributions to physics is not merely a theoretical discovery, nor is it akin to the experimental discovery of the laws of motion of physics. My contributions to physics exist in a separate category, one called extreme scale experiments in computational physics. It has mathematical physics and supercomputers at its foundation. I contributed to physics by experimentally discovering how to massively parallel process across a new internet that's a global network of processors. Theoretical physicists, the likes of Albert Einstein, cannot solve a system of coupled, nonlinear, and time-dependent partial differential equations that in theory can be exactly solved by executing an infinite number of floating point arithmetical operations. That set of infinite calculations is at the calculus core of a general circulation model that's running across a global network of 64 binary thousand commodity processors, or across a global network of as many identical computers. The necessity to execute extreme scale computational physics codes stimulated the development of the modern supercomputer that computes across processors and computes in parallel. That historical milestone in extreme-scaled computational physics was crossed at 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the U.S. Independence Day. The milestone was crossed when I experimentally discovered that the slowest 65,536 processors in the world can solve the toughest problems in computational physics and solve them faster than the fastest supercomputer that cost the budget of a small nation. Prior to that experimental discovery, computational physics codes were limited to the resolution of only one processor that is not a member of an ensemble of processors, instead of to the resolution of my ensemble of 65,536 processors. My experimental discovery of massively parallel processing enables extreme scale modelers to derive detailed information from petroleum reservoir simulators and from general circulation models and from the most computation intensive codes in computational fluid dynamics. Conversely, the resolution in computational physics is now limited by the level of parallelism within the modern supercomputer. My technological quest for the fastest parallel processing supercomputer was not an 8-year-long sprint. That scientific quest was a 16-year-long parallel processing marathon across mathematical physics, across physics and supercomputing. I began programming the world's fastest supercomputers on Thursday, June 20, 1974. I began supercomputing in the Computer Center at 1800 Southwest Campus Way, Corvallis, Oregon, United States. On a typical day, I worked for 3 hours from 4 a.m. to 7 a.m. as the janitor at the ceramics building that was a short walk from the Computer Center. The rest of the day, I was more likely to be inside Kidder Hall, the mathematics building at 2000 Southwest Campus Way, Corvallis, Oregon, United States. The mathematics building was a shouting distance from the computer center that housed the supercomputers that I was programming. When I began supercomputing, massively parallel processing, the technological engine that powers the modern supercomputer, was the most beautiful theory in supercomputing. Like any theory, massively parallel processing in the 1980s was an idea that was not positively true. The June 20, 1990 issue of the Wall Street Journal recorded that I, Philip Emeagwali, conducted a never-before-seen supercomputer experiment and did so across 65,536 commodity processors. In that supercomputer experiment, I confirmed massively parallel processing as positively true. In that supercomputer experiment, I upgraded massively parallel processing from a theory to a discovery.
Insightful and brilliant lecture.